it. We're going to be going and finishing this today. And just to kind of remind ourselves of what we're trying to do, right, F equals MA. And we're doing that on a little tiny cube of fluid that's moving in some larger velocity field, some larger fluid flow. So this is one little speck of particle of fluid in a larger velocity field. We're trying to build up equations for what does the force on that little cube of fluid look like? What's the mass of it? What's its acceleration look like? So what we built up last class, and it took us the whole time. So it's been taking some time, and we'll really spend the rest of today on the rest of this. We looked at what does acceleration look like? Remember, I think a useful analogy is thinking about temperature, a temperature field rather than a velocity field. And I think temperature is easier because temperature is just a scalar, it's just a number, or velocity is a vector, so it has kind of this added wrinkle of making it harder to think about. But for example, we did this problem, okay, if you know you're a little dinosaur flying in an airplane and you know how the temperature changes as you go north, you know how the temperature changes as you go up in elevation, then you can say, how is the temperature going to be changing for me? Similar to like, you know the temperature in this building versus outside, so you know how the temperature is going to change if you walk outside. Right? You're looking at this, what does the temperature surrounding me look like as I move in some space? It's going to be the same kind of idea with fluids. The temperature around you, the velocity that you have, that you're experiencing, is going to change whether you're at location A or location B or location C. Just like the temperature around you changes whether you're in this room, whether you're out in the hall, maybe it's a little different. If you go outside, it's way different. So your temperature that you're experiencing at a given moment in time depends on where you are. The other thing that it depends on is not just where you are, but if there are any changes happening at the location you happen to be at. So like for instance, if somebody opens a window, it gets colder in here. So you're going to be at the same position, but you experience a temperature change. If you're a fluid and like somebody cranks a valve open and the velocity goes up everywhere, there's also going to be that component. So it depends on where you are, but also if there are any local changes to velocity. We kind of described it. Okay, so it matters. You have like part is you moving around to different locations. This part is like weather changes. If there are any weather changes, that's going to change the temperature that you're experiencing. So we have kind of those two different components. It looks a little ugly when we're talking about velocity fields because velocity is vector notation. So we have this whole term which we call the convective flow term. That's velocity changes that you might experience because you're moving from location A to location B to location C. As you're moving in the fluid, you're going to be changing velocity, you're going to be accelerating. And then this term is local acceleration. This is the term that you're experiencing velocity changes because like somebody's opening a valve and the velocity everywhere is going up. So this gives us our acceleration term, our A, how our particle of fluid is accelerating in our larger velocity field. What we're going to work on today is forces and M. So mass is the easy one. So if I'll scroll back up to the very first page. If we look at this little chunk of fluid, what is its mass? Well, its mass is density times volume. So its density is the density, rho. What's its volume? Just dx, dy, dz, right? The side lengths. So the mass of the particle, the mass of our fluid particle, mass equals, okay, so it would be, you know, something like this. Integrating density over volume, we could write it fancy like that, but this just mass equals rho dx dy dz, right? And this is just the volume of our cube. Okay, so done with mass. So we're done with mass, we're done with acceleration. Now let's do forces. So again, looking at this little fluid particle, what forces, what like broad types of forces could be acting on it? And we want to be kind of as general as possible. So there could be like shear stresses that are acting on the fluid. Any other types of forces that could be acting on our little fluid particle? Pardon?
Normal forces?
Yep, so a shear stress, we could also have normal. So these would both be, I'm kind of jumping ahead, but these are both under the broad category of surface forces. What would be our last category of forces? Body forces, right? Like gravity. Okay, so we have, again, these kind of two broad categories, body forces and surface forces. We have shear stress, normal stress, and gravity. Okay, we could have other body forces. We typically don't. We potentially could. If we did, then things would get even uglier than they will already. But most cases, we don't have like magnetism or something like that. So if you flip to the next page, we're just looking at this is a diagram that we looked at earlier in the class when we were thinking about forces, shear stress, normal stress, and the notation that we were going to use. If we look at, okay, the kind of the base simplified equation for the net forces acting on our fluid, it's going to be body forces plus surface forces. We'll look first at just the x direction, and then we'll say, okay, the y and z are pretty easy once, like if you get x, y and z follow pretty easily. So we'll just look at x. So if we look at the total forces in the x direction, that's going to be equal to the body forces plus surface forces. So a differential force element in the x direction. The force that we have on our little tiny cube is the body forces on that little tiny cube plus surface. Okay, in almost all cases, body forces, just gravity. That's the one that we'll decide, we'll look at. So what are the force due to, what's the force due to gravity on our little tiny cube? Mass times gravity, right? So our differential force is mass times gravity in the x direction, which is equal to density times gravity times volume, dx dy dz. Okay, so the body forces are pretty straightforward. It's mass, okay, we write it a little weird. It's mass times gravity. Surface forces is where things get a little bit hairier, because if we look, okay, we want to find all of the surface forces that are acting in the x direction, that direction. So let's circle and look at what those ones could be. This one's acting in the x direction, that's a normal stress. This one's acting in the X direction. But then we also have this guy up here on top, this guy on the bottom, this guy on the front face, and this guy on the back face. So we actually have all six of those things acting in the positive or negative in the X direction. Let's look just at, I'll erase this and, or let me just circle in a different color. So let's just look at these two. So what we care about, we look at those. When we're looking at like the forces on a fluid, if you're pushing, with 10 newtons on one side and 9 newtons on the other side, your net force is 1 newton. If you're pushing with 999 newtons and 1,000 newtons, your net force is 1 newton. So we don't really care about the exact value of either side. We care about the difference between the left side and the right side. And same for the top and the bottom. We don't actually care about the exact value at the top and the bottom. We care about any differences between the top and the bottom. If we look at like how that's going to work, so we're going to care for sigma. I guess I'll write it. We're going to be moving from this side at, we'll say, some value x, all the way over to this side dx later, right? Moving from the left side kind of to the right side. If we're looking at the top and bottom surface, we're going to be moving from this side, we'll be moving up and look at that side, which is their dy apart. And the same thing, we could move from like the left side and the right side, or I guess the front and the back is going to be z and dz. But for all of those, we're only going to care about like what's the difference between the opposite sides. So let's write what that would be. So our differential surface force is sigma on one side minus sigma on the other side. Okay, at x and at x plus dx on the other side. That's the stress. To convert from stress to a force, you need to do, right, a force is a stress multiplied by an area. So again, let's look back up. So we're looking at sigma. So we're looking at, that's acting on this area and this area. So those areas, this is dz, and this is that side is dy. So the area is dy dz. So, okay, so sigma xx times dy dz. Okay, now we have to do, okay, plus the top and the bottom. That's tau yx evaluated at y at the bottom minus tau yx evaluated at y plus dy times the top and bottom area, which is going to be dx dz. So this is dx dz. Plus, and I wrote too big, so we'll jump down here, tau zx, z minus tau z x, z plus dz, dx dy. So that's our differential force element, comparing the stress at the top and the bottom times the area left and right times the area front and back times the area. What we're going to do is simplify these. simplify this equation because we can compare the stress on one side compared to the stress on the other side, right? That's going to be the stress on one side and the stress on the other side. They're not totally unrelated because the stress on one side is equal to the stress on the other side plus the difference in those two. So that's what we're saying here. So the force at position like x plus dx, y plus dy, z plus dz, that at n plus dn is equal to the stress at n plus the rate of change in the n direction. So like for, again, just to come back up here for sigma, the value on the right side here is equal to the value on the left side, what it was here, plus, like, say it's changing like that. So this is the change, right? So if you came in at this side with a certain value and it changed by 1, and you're coming out at the right side with the value of like left side plus 1. So we're going to write it in kind of a weird differential notation kind of way, where this is, okay, the value on the right side equals the value on the left side plus how much it changed. This differential, that's the rate of change times dx, which is the distance over which you change, right? The distance from the left side to the right side. So it's kind of a weird way to write it, but it will help us simplify things. We could write the same basic equations for tau. So tau, write these kind of small in the side because otherwise you won't have room for everything. So tau yx evaluated at y plus dy equals tau yx evaluated at y plus d tau yx dy times dy. And you could write tau zx at z plus dz, zx evaluated at z, plus how much it changed, tau zx dz times dz. Okay, so what we're going to do, and again, we'll look at the sigma part first. But what we're going to do is take this equation and those other two that we just wrote and plug them in up there. So if we plug this equation in up there, or I guess plug in this left side, or sorry, right side. So we plug that side in up there, we can see the handy thing is this will cancel out with that. Right, so we'll be left with just the d sigma xx, partial sigma xx, partial x times dx. And you can see that we'll have a dx, dy, dz. Dx, dy, dz. We'll do the same thing, okay, with this next one. We'll have, so we're taking this guy here, plugging that in there. This will cancel out with this, and we're left with partial tau yx, partial y, dx, dy, dz. And the same thing with the last one, partial tau zx, dz, dx, dy, dz. So we can write all of this equation, dfsx equals partial sigma, partial x, plus partial tau yx, partial y, plus partial tau zx, partial z, dx, dy, dz. Okay, so these like individual partial differentials, we're not going to solve them in detail, but I will just note as we're looking at these, okay, we could look at tau yx equals mu du dy. Right, that would be our equation for that shear stress. Right, it's equal to viscosity times the slope of the velocity. So if we wanted to, for example, like take this here and plug that in right there, we'd still have the viscosity is just a constant, so that's fine. It would just stay there. And we get a second derivative of the velocity with respect to y. Right? We'd get a d squared u dy squared. Same kind of thing would happen with the z part. The sigma xx is going to be a little bit different because one of the things that's going to be different about that is you could have pressure gradients, right? So like pressure could be pushing on one side. So pressure can't push, pressure always pushes directly in. So the only way for pressure to be pushing in the x direction is if pressure is pushing, right? Force equals pressure times area, and you have a force on this side, F equals pressure times area. So you could have, okay, pressure is bigger on one side than the other side. So we're going to have like this viscosity term with what's the velocity gradient squared, sorry, the second derivative of the velocity, and we're going to have pressure terms. So I'll just write, again, we won't derive this in detail because I think we got close enough, and it actually gets a little bit messy if you do in detail. But it's going to be minus dp, so pressure plus viscosity times now all of these directions, d squared u dx squared plus d squared u dy squared plus d squared u d z squared. And all of these have a, just like they did up above, they all have a dx, dy, dz part to them. Okay. And then we're pretty much there. So let's look at what, so we're trying to do, right, f of x equals mass times acceleration of x. I'll write the acceleration of the particle. So forces, okay, we can have two different forces in the x direction. So that's f bx plus f sx equals mass times, again, acceleration of our particle. And then, again, if we look back at our different terms, so the terms on the left-hand side, the two forces, this force has a dx, dy, dz. If we go back to our body force, that has a dx, dy, dz. So we have dx, dy, dz on both of the left-hand side terms, and a dx, dy, dz on the mass. So we end up having this dx, dy, dz term on both that term, and the mass. So we're going to be able to divide out by dx, dy, dz. So what we'll end up with is rho gx, that's our body forces, gravity, minus, we'll write the surface forces, d squared u dx squared plus d squared u dy squared plus d squared u dz squared. So that whole big thing, surface forces. So that's F equals M, just density, the easy one. And then A. So A was, we scroll up again. A was this whole big funny thing, right? This was the acceleration of our particle. So we'll plug in just the x component of that. So instead of velocity vector, we'll just have the x component. So if we plug in A, that's du dt plus u du dx plus little v du dy plus little w du dz. So this whole big thing is ax, acceleration of our particle. Okay, and then lo and behold, we've made it. So if you flip over to the last page, okay, so we can write out, that was just the x direction. So the real fun begins when you have to do things in 3 dimensions. So if you look at this, we have a component up top. This is the x dimension. It's, okay, this is A. This is MA equals F, how they have it written, instead of F equals MA. Same equation. This is the X, this is the Y, that's the Z direction. So you have similar equations, F equals MA, because everything's vector, so it's in all three directions. And then you also have this one, which is continuity. Conservation of mass. So you have 3 different equations to handle F equals MA, and you have 1 equation for conservation of mass. All 4 of these guys go together. Right? So if you want to understand how forces and fluids work together, how fluids respond to forces, what you have to do is solve all 4 of these equations simultaneously. Sounds like fun, right? So we have 4 nonlinear PDEs. They're coupled, meaning like, right, if you look at them, okay, this top one has a U in it, a V in it, and a W. This guy has U's all over the place, but it also has a V and a W. Has some U's over here. This one has V's all over the place, but it also has U and V and W. This one has pressure, this one has pressure, this one has pressure. So we have 4 variables. Our variables are U, V, W, and pressure. So all 4 components of the velocity and pressure. We actually have, it's even more fun than just 4 nonlinear PDEs. It's because these 3 of them here, those are all 2nd order PDEs, right? They'll have like a partial squared. So that's fun. They're not even just like nice 1st order PDEs. We have 4 variables. We actually also have 4 dimensions. So these are and all of our variables depend on X, Y, Z, and time in general. So we have 4 variables, each a function of 4 variables. So if we wanted to solve this, right, and this is where it gets super fun. So you need an initial condition for each of those 4. So 4 initial conditions. You need a boundary condition, 2 boundary conditions for each spatial variable. So for X and Y and Z, you need 2 boundary conditions, but you need that like for each. So you need 6 boundary conditions for U, 6 boundary conditions for V, 6 boundary conditions for W, and 6 boundary conditions for pressure. So we have 4 nonlinear PDEs. We would need 4 times 1 initial condition and 6 boundary conditions. Right, because we have this partial squared, partial squared, partial squared. So then we would need 2. So you can see very quickly, this gets to be lots and lots of fun to solve. So what do we do about it? Well, we don't solve it, right? We can solve it. We will solve it. We'll go and solve it for very simple cases where we can cross out everything but like one thing, or maybe 2 things. So that's how we'll actually solve it. If you're a super great mathlete, then you can cross out everything but like 3 things and still solve it. So, okay, you can do it somewhat. It gets even more fun if you plug in like, you can do this actually, but if you have like an energy term in there too, like things are getting heated, then you would have the conservation of mass, F equals ma, and you'd have another set of 3 equations for conservation of energy. You'd have to solve all 7 of those simultaneously. So that's when things get even more fun. So right, practically, we don't actually solve these. So we can solve. So we can solve for very simple cases only. We can solve, like us in this class, I mean, like this we is like anybody can solve for only a very simple case. We will only ever solve for like a very, very, very simple case, which should give you some comfort at night so that you don't have to, do anything too crazy with PDEs. So we will only solve for like the almost absolute simplest case, and even then it'll still take us some some figuring out like what terms are going to be 0 and how do I actually solve these. But I think you'll get a taste of how we do that. One of the cool things about this, right, is if we can solve these, then we know velocities, u, v, w, and pressure everywhere. Exactly. So if we want to calculate things like forces, we can do that. If we want to like watch what velocities are everywhere, like we know that. We know everything exactly. So when you can solve it, it's really, really powerful because you know all of this stuff exactly. So we'll see a little bit how that works. Again, in simple cases, like if you want to calculate flow rates, if you want to calculate forces acting on objects, if you want to calculate how a fluid particle moves over a certain amount of time, like velocities and pressures and all of the stuff everywhere. So you can just do it and you have all of the information. If you can't solve it analytically, you can still solve it actually pretty easily numerically. So you don't always need an exact solution. We'll get a couple simple exact solutions, but if you ever do a fluid model or a fluid simulation, this is what you're actually doing. You're solving numerically So numerical solutions to these equations are the foundation of what we would call computational fluid dynamics, or CFD. So if you ever run across CFD, what you're actually doing in any CFD model, you're setting up the system and you're saying, hey, computer, take these 4 equations and these 4 unknowns and approximate them numerically. Any CFD model, any computational model like that is only ever going to be an approximation of reality because it's a numerical solution. So it's right, if we could get an analytical solution, then we would know exactly. We can only do that in like the most simple cases. So then, okay, we need a numerical solution, and then we only ever get like part of the way there. We can get pretty accurate stuff. We'll talk as we continue on, we'll talk a little bit later about like where kind of numerical simulations have problems. Under what conditions are they going to have problems? Under what conditions are they going to give stuff that it's like if you squint, it's close to what's happening, but it's not exactly what's happening. So we'll talk a little bit about what that looks like. So one of the reasons I wanted to go through and spend really 2 full days deriving equations that you won't have to go back and like do the derivation again is I think it's useful to be able to look at these 4 big ugly equations and say, oh, that top one, that's conservation of mass, that's pretty easy. And those bottom 3, those are just F equals ma. Right, they're big and ugly, but you guys are used to F equals ma. You know how that works. That's all that this is doing. One of the things that we're going to do starting Friday is not start solving these yet, but we'll say, okay, if we look at the right-hand side here, that's gravity, that's pressure. These terms are all from viscosity, mu. So you can, right, just like we've done when we've looked at forces on a control volume and stuff, we said, well, in this problem, gravity's not acting in the x direction, so we don't really need to care. In this other problem, pressure is the same, so we don't need to care about pressure. So we can do some of those same types of simplifications. The first one that we're going to do is say, all of these, the ugly part of this equation on this side, like these first 2 are really pretty simple. The ugly part is all multiplied by viscosity. So what happens if viscosity is small? Maybe it's really close to 0. Then that whole ugly part goes away. And we can look at what happens. What like physical systems would that approximate? Well, air is pretty small viscosity. Right? You like move your arm through air. It can cause forces on things, but it has a really low viscosity. So a lot of aerodynamics pretty well approximated by these equations with that part crossed out. So we'll look a little bit at how that happens. It also happens, if there's like flow where your velocities are really high, something like that, like things are moving really fast and viscosity is just not that important. So even like in water, if you want to look at water shooting out of a fire hose or something like that, viscosity is not super important. So you can say, okay, we'll not care about it and see what happens. So we'll look a little bit at how that can teach us some things and give us some insight into how flow systems work. But I think seeing it all split apart like this, it will give us some insight into how some of these things actually work and behave. We'll be able to calculate things exactly, like, when we looked at flow in a pipe, we could see what does the flow look like. Like this is where that all comes from. You can look at flow rates and pressure gradients and velocities and all of these things exactly. So we'll pick up with that on Friday. On Wednesday, next time we meet, we have an exam. So I just wanted to, I know I've sent out some info on this, but just to kind of briefly talk about it and then open it up for any questions that you might have. Right, we said 70% of the exam about, because that's what so the exam is going to be 4 questions. Most of it is going to be on, so plus the integral over the control surfaces of rho v dot dA. So that's conservation of mass, Reynolds transport theorem, and this is d dt. The rho, right? So not 0, f. Okay, so these equations should hopefully be familiar to you. Working with those 2 equations is going to be about 70% of the exam. I think it's exactly 70% of the exam. Could be a little off on that. I don't remember. About 70%. 2/3 to 3/4, somewhere in there. So there will be one problem on the exam where at least one part of it actually makes you solve either that integral or that integral. So a lot of times we've said if it's uniform velocity, then we can just do, velocity times area, or velocity times density times velocity times area. Like we can change it from an integral to a sum. Most of the time you will be able to do that. There will be one time where you have to actually go through, one of the problems will make you actually go through the integration. So make sure you look over that. There's an example when we first introduced this top equation. In our notes, there was an example that we went over in class that would be a good one to look through, where we did that integral. There was also a homework problem on, I think, homework 4, where you did both of those. So those would be good ones to look over. And then the other one is, like this tends to be the top equation, conservation of mass. There could be a problem specifically on conservation of mass, or that could show up as part of a subpart of an F equals ma problem, force problem. The force one, go back over and make sure you look over and can figure out how to rationalize your way, what forces are acting on the control surfaces and how do I handle signs and those kind of things. I think are all good to study. These only inertial control volumes. So we're not going to do anything with an accelerating control volume. Only stationary or moving at constant velocity. The other 30% of the exam v dy plus d z equals 0, right? The continuity equation, or d psi minus d psi dx equals v. So it's going to be looking at those things. right? I could be asking something like for the top one, continuity, given this velocity field, is it an incompressible velocity field? Is it possible? Or does it break conservation of mass? So I could ask a question like that. You did a couple on the last homework. I could also ask a question like we did on the last in-class assignment where, I know the U component, what would be a possible V component? So you could kind of go either way on that. The stream function, I could say, here's a velocity field, what's the stream function? Here's a stream function, what's the velocity field? I could ask for what's the flow rate between 2 points. Right, so that would be like Q equals psi2 minus psi1. Flow rate is the difference in that. So I would look over, again, like kind of this last homework and that last in-class assignment would both be good things to study from for that section. Like I said, those are going to be, I would say they're kind of at a similar level to what the in-class assignment was. Where can you work backward and forward with some of these different definitions and kind of work through with the math of some of these things. So that's going to be the exam. It will be Wednesday. Like I said, there are 4 problems. You can have one handwritten note sheet. I don't care if you write on both sides. You should for sure have like the equations that I've written down here somewhere. Other than that, I think there will be unit conversions and stuff, and I think a lot of the other stuff I have laid out in the email I sent out last week about the exam. But are there any kind of last minute questions that anybody has? Yeah.
Any specific example problems, or like would that be a good way to check for example problems in the book?
Yeah, the example problems in the book would be a good ones to like practice, or if you can find one similar. I mean, the homework problems I chose because I think those are good problems. So those are a good place to start. I'll open up the solutions for this last homework today so that you'll have those to look at. But hopefully some of the example problems in the book I think are pretty good. But yeah, all of those, or like find, we did this problem, here's another problem from the same section. If you want to go through and do an example problem like that, it's not a bad way to study, at least like see if you can set it up and think your way through that part. Because I think especially for those top ones, setting it up is often the hardest part anyway. Yeah, so I think if there aren't any other questions, we'll stop there and we'll see you guys back here Wednesday for the exam.